All right, welcome back to the Quantum Thread, everyone. Today, we're diving into something that sounds straight out of a sci-fi novel, but it's very real and honestly incredibly exciting. We're talking about quantum computing, specifically Vogon's Quantum Virtual Machine, or QVM, and their Vogon Distributed Decentralized Quantum Ledger Database, DQLDB. Susan, Elizabeth, thanks for being here.
Happy to be here, Paul. It's a fascinating area, and Vogon's approach is genuinely innovative.
Yeah, the idea of making quantum computing something you don't need a super secret lab for is pretty mind-blowing. It really changes the game.
Exactly. That's the core of it, right? So let's start with the QVM. Susan, for those of us who aren't quantum physicists, what exactly is a quantum virtual machine?
Great question, Paul. At its heart, a quantum virtual machine, or QVM, is a software platform that lets you write, test, and run quantum algorithms using a classical computer. Think of it like a simulator. You don't need actual quantum hardware, which is incredibly expensive and rare, to start developing for quantum. It simulates what a quantum computer would do, though it's important to note that while it provides a valuable approximation, the performance and results can differ from those on actual quantum hardware.
So basically, it's democratizing quantum development. Like if I'm a developer, I don't need to wait for a quantum computer to be in my server room. I can just start coding for it now.
Precisely, Elizabeth. It removes that huge barrier to entry. Vogon's QVM in particular is designed to be very developer-friendly. It supports a full quantum stack, meaning it works with popular quantum programming languages and frameworks like Qiskit, Cirq, OpenQASM, all the big names, so if you're already familiar with those, you can jump right in.
That's huge, because I imagine the cost and complexity of real quantum hardware is just astronomical right now. So this lets people experiment and build, and then presumably when the hardware catches up, their work is ready.
Absolutely. And it's scalable. Vogon's QVM can simulate up to 64 qubits, which is quite significant for a simulator. This allows for testing more complex algorithms than you might expect. Plus, it enables what we call hybrid quantum classical algorithms, where part of your computation runs on the QVM and part runs on traditional classical processors.
That hybrid part sounds really useful, especially for problems that have both classical and quantum elements. Like, you don't want to throw out all your classical algorithms just because quantum is new. You want them to work together.
Right, it's about integration, not replacement. Now this QVM runs on something else Vogon has developed, which is even more intriguing, the Decentralized Quantum Ledger Database, or DQLDB. Elizabeth, can you unpack that acronym for us? Because quantum databases and decentralized ledger are two very powerful, very modern concepts.
It's a mouthful, I know, but it's also revolutionary. Imagine a blockchain, but specifically designed for quantum data and with quantum-level security. That's DQLDB. It's a distributed, decentralized database that stores and manages quantum states, entanglements, and other quantum information, not just the results of quantum computations. It's built from the ground up to understand and handle the unique properties of quantum information.
Okay, so a blockchain for quantum. What makes it quantum native?
Traditional databases aren't equipped for that. Vogon's DQLDB doesn't just store bits, it can manage qubits, superposition, entanglement, and the results of quantum computations in a secure, immutable ledger.
And the decentralized part means there's no single company or server controlling all this sensitive quantum data, right? That sounds like a massive security boost.
Exactly. No single point of failure, no single entity that can be compromised to gain access to all the data. This provides incredible resilience and security. And it's not just decentralization. Vogon uses some very advanced cryptographic techniques here.
Like what? Because when we talk about quantum and security, my mind immediately jumps to things like quantum key distribution and unbreakable encryption. Is Vogon DQLDB leveraging that?
It goes beyond just basic quantum cryptography, Paul. Vogon DQLDB supports a feature called homomorphic encryption. This is incredibly powerful. It allows computations to be performed on encrypted data without ever having to decrypt it. So your data can remain encrypted throughout its entire life cycle in the database, even when it's being processed.
Wait, so if I have super-sensitive quantum data and I need to run a calculation on it, the calculation happens while the data is still scrambled? That's incredible for privacy.
Absolutely. Imagine in drug discovery, where pharmaceutical companies want to collaborate on research using highly proprietary molecular data, but they can't share the raw data. With homomorphic encryption, they could potentially run quantum algorithms on that combined, encrypted data and only see the results, without ever revealing the underlying sensitive information.
That's a game changer for industries dealing with highly sensitive information. Finance, healthcare, defense, you name it. So we have the QVM for developing and running algorithms and the Vogon DQLDB for securely storing and managing quantum data. How do they interact? How does the QVM leverage Vogon DQLDB?
They're designed to work hand in glove. The QVM acts as your interface to the quantum world. You write your quantum program and it executes on the QVM. But when that program needs to store quantum states, interact with a shared quantum data ledger, or retrieve previously processed quantum information, it connects directly to the Vogon DQLDB.
So you're building a quantum application on the QVM, and Vogon DQLDB becomes the secure, decentralized backend for all your quantum data needs. It's like a full quantum cloud environment, but without the central point of control.
Precisely. It creates an end-to-end ecosystem. Developers get the tools to build, and they get the infrastructure to manage the data securely and resiliently. It means you can develop quantum applications that are inherently decentralized and privacy-preserving from day one.
That's genuinely impressive. Let's talk about some of the actual applications. Susan, from your perspective, what kinds of problems could this combination of QVM and Vogon DQLDB start to tackle right now, or in the very near future?
Oh, the possibilities are vast. We've already touched on drug discovery and material science. Imagine simulating molecular interactions at a quantum level, or designing new materials with specific properties. That's a huge one. In finance, think about complex financial modeling, risk assessment, or even detecting sophisticated fraud patterns that current classical computers struggle with.
So, optimization problems basically, but at a scale and complexity that's currently impossible.
Exactly. Optimization is a huge area for quantum. Supply chain logistics, route optimization, even things like traffic flow management in smart cities. Then there's AI and machine learning. Quantum machine learning algorithms have the potential to process vast datasets and find patterns far more efficiently than classical methods, leading to breakthroughs in areas like image recognition or natural language processing.
And don't forget cybersecurity. With the Vogon DQLDB's quantum cryptography and homomorphic encryption, it provides a level of data security that's incredibly robust, even against future quantum attacks. It's essentially future-proofing your data infrastructure.
That's a critical point, isn't it? Because there's this looming threat of quantum computers breaking current encryption. So, developing quantum-safe solutions now is essential. How accessible is this for an average developer who might be intrigued but has no quantum background?
Vogon's whole philosophy seems to be about accessibility. By providing the QVM that runs on classical hardware and supporting existing quantum programming frameworks, they're significantly lowering the barrier. You don't need a PhD in quantum physics to start experimenting. You can learn the quantum programming paradigms, understand the basics of qubits and gates, and then start building on the QVM, just like you would learn a new classical programming language.
I think it's about providing that on-ramp. Right now it feels like quantum computing is behind a massive locked door. Vogon is essentially giving developers a key, even if it's for a simulated environment. It allows them to get familiar with the layout before the real thing becomes widely available.
That's a brilliant analogy. So, looking ahead, what do you see as the biggest challenges or the most exciting developments on the horizon for Vogon's QVM and DQLDB?
The biggest challenge, as with all quantum computing, is scaling and error correction. While the QVM can simulate 64 qubits, real quantum hardware is still limited and prone to errors. However, by enabling widespread development now, Vogon is helping to build the talent pool and the algorithms that will be ready when the hardware catches up. The Vogon distributed DQLDB also has to continually evolve to handle even more complex quantum data structures and ever-increasing transaction volumes, while maintaining its speed and low latency.
I'm excited about the real-world impact. As more developers use the QVM, we'll see more innovative applications emerge. I think the integration with existing enterprise systems will be key, showing how these quantum capabilities can augment current business processes, not just live in a silo.
It sounds like Vogon is really building a foundational layer for the quantum internet, or at least a quantum-powered data economy. The ability to manage, store, and process quantum-secure data in a decentralized, privacy-preserving way is truly visionary.
I agree. It's not just about running algorithms, it's about creating a trusted environment for quantum data, and that's something that will be absolutely critical as quantum technologies mature.
Yeah, and I think the decentralized aspect can't be overstated. In an age where data privacy and control are paramount, having a quantum-ready database that doesn't rely on a central authority is a huge selling point.
Well, this has been an incredibly enlightening discussion. It's amazing to see how Vogon is pushing the boundaries, making something as complex as quantum computing accessible and secure. Susan, Elizabeth, thank you so much for breaking down the quantum virtual machine and the DQLDB for us today.
My pleasure, Paul. It's a field I'm very passionate about.
Thanks for having us. Hopefully we've piqued some interest out there for developers to check it out.
Absolutely. And for all our listeners, if you're curious about quantum computing, Vogon's QVM and Vogon Distributed Decentralized Quantum Ledger Database, DQLDB, are definitely technologies worth exploring. It might just be the future of how we compute and manage data. Go to vogon.cloud for more information. Thanks for tuning in to the Quantum Thread, and we'll catch you next time.